All right, good morning, everybody. Today's lecture is going to be a follow-up for the probability of detection from the introduction lecture last week, and then we're going to get into ultrasonic testing methods. So last week we discussed the probability of detection confidence levels and how it's generally based on statistics. So it's unique to the type of non-destructive testing technique that you're using, and it's unique to how many samples you're able to inspect at one time. So we had discussed the aerospace blade example with the cooling channels, and I wanted to actually bring this in. This is actually one of the blades, and in the what's known as an MRO, maintenance and repair office, that's where when commercial airplanes need to go and have their engines torn down and checked, that they take the engine apart and then they'll do the inspections and make sure everything fits back together. So the cooling channels on here that I showed you the video with last week, you're able to get an idea on the orientation on where they place these. And if these cooling channels aren't here, for the turbine section, at least in the airplane engine, the plane operates beyond the melting point. This is should be an Inconel or typically a nickel-based superalloy. The notation on that blade deals with during the inspection, they found some anomaly during the repair. So that's just the writing from the inspector to remove that from service. So I had asked you guys last week to pick one of the journal articles that I had posted on Stellar. Did any of you have any questions from the article you selected of reading? Did any of you read an article or no? So next time, make sure you read the article. All right, so following up from last week, non-destructive testing. The geometry of the part, location of the area, and the type of material, okay? This goes in, what happens with your non-destructive testing technique, it deals with the field of fracture mechanics. So when you have potential for surface or subsurface flaws in the component, you want to be able to predict how much time that component will have before the subsurface or surface crack grows to critical length. So what we have here is what's called a CT compact tension specimen, and this is for fatigue testing where you will do cyclic loading. And what happens is the component goes into a universal testing machine, it gets gripped on either side here, and it actually forces this crack notch over cycles to see when that crack initiates, and then at certain point after the crack initiates, the propagation rate, so it's called fatigue crack propagation rates. So I'm not sure if you guys are mechanical engineers or material scientists, but the fracture mechanics is very important for life prediction for structural components. So based on what we discussed, yeah.
The CT sample is for mode 1 fracture mechanics. Is there any tests for mode 2 or mode 3 that you know of?
Generally what they do with the CT sample, they'll make mathematical corrections for mode 2. Mode 3 is separate, so there's different types of samples. You can actually have similar to like a dog bone tensile specimen. And what I've seen on some samples is they actually will insert either a borescope camera or some small type of camera, and then they will zoom in on that notch. So what they can actually do is map and track with respect to how many cycles that they've put onto that sample to try to correlate to different modes. So one of the things we're dealing with here with non-destructive testing is depending on which material you're selecting for the structural component, the processing involved. So whether we're dealing with the example here of nickel-based superalloys, whether we're dealing with aluminum components that come out of a smelter, whether we're dealing with plain carbon steel or some other type of material, for metallic alloys, one of the main issues that you can get is segregation while it's in the melt stage. So what you're seeing in this image here is there's actually what you're seeing is a freckle defect on the bottom there. So in the melt stage, if you don't have alloys that can be in perfect solid solution with each other, you can get segregation. And in steel plants, this is one of the big problems. They perform a technique called hot topping of the billet. And they already know that there's segregation for steel alloys. So what they do is they use gravity to their benefit, and they say that the alloys are generally to statistical reliability confidence, it will segregate to the top or bottom 7% of the billet. So what they do is they scalp that off before continuing it processing, and that goes back in and gets remelted and gets reused. So there are quality assurance, quality control techniques involved in the steel plants to address these. But what happens is if there are embedded inclusions further within that billet, those are ones that can get through to when you start milling and machining to get to your final component.
If these are super alloys, though, a lot of them are single crystal casts. So do you get the same variations in properties like that if you actually cast it as a single crystal?
Casting as a single crystal, you won't get segregation.
Okay.
But if you have an alloy, so you could have an aluminum alloy that is not cast as a single crystal, but you can still get, in the lecture last week, that was the image, it was what's referred to as a hard alpha inclusion. So for aluminum and titanium, even though you can still make single crystal TI-64 blades, if you're not talking about aerospace, if you're talking about titanium alloys for another industry, you can get inclusions for those components. So the main one, porosity, subsurface porosity, for what we're going to talk about today. For ultrasonics, the main consideration and the main advantage of the ultrasonic technique over an eddy current or a magnetic particle or X-rays is the fact that you can penetrate deeper into thicker samples. So if you're dealing with a micro electromechanical device, all right, you're concerned with micro scale, nanoscale. For the macro scale, when we're talking about something that is going to be feet in thickness, so I-beams or structural components for buildings, the size of the component leads to using ultrasonics because you need to penetrate deeper through the metal. So variables relevant to the probability of detection, okay? There's not just material considerations based on the alloy selected. With non-destructive testing, there's considerations on the sensitivity of the equipment you're using. So for some, sensitive government type projects, the electrical noise from the equipment selected can be enough to lead your signal to noise ratio to be inadequate. So there's NDT equipment variables, there's the procedure variables on how you exactly go about inspecting the component. So one of the examples we're going to show in the later slide, it deals with immersion ultrasonics. And for that, you actually have to have the scan plan on which locations you want to scan first. Otherwise, you won't get 100% coverage of the component. So the two I have highlighted here are calibration variables and the acceptance criteria decision variables. These are generally, for these techniques, a human has to interact with the equipment. So when you see human factors or if there is missed detection, sometimes they can come back to, was the calibration performed properly, or who decided what the threshold for the sensitivity for the flaw size would be. So this leads to what we talked about last week. You can have a missed indication, so when there's an actual flaw there and you miss it, but you can also have a false positive indication. And for high value structural components, the cost to pull out a structural component due to a false positive indication is sometimes even more in a monetary wise, because you have to take the part out of service and it leads to business interruption for the component. What you're going to see in this image here on the right, that is an ultrasonic pulse echo transducer. So what you're seeing is that there's certain inputs, all right, from the NDE equipment to the part that's under inspection. So we're not going to go into super depth on selection of different types of transducers, but I do want to hand this out because you hear ultrasonic testing and you think it's just, all right, we put the material and we put the probe over it. The variables that are all as important are the selection of the probe, the selection of the wedge, and you can go through this booklet here and you can see how detailed it gets. There's certain types of specific probes for specific components due to geometry restrictions. There's certain types of transducers for specific alloys. So there's a lot of material considerations that come about that could be its own class, but it's something that you should just be cognizant of. So back to the probability of detection. What you're going to see here is essentially the feedback loop when you're doing inspection and tying it in for probability of detection and to get to a specific confidence level. So if it's for a critical structural application, the metric that the industry has approved is that 95% POD at a 90% confidence level. All right. In order to get the confidence level up, you can either do you can test more components, or you can try to show that you can detect a smaller flaw size more reliably. So there's two ways to go about that. What you're seeing in the bottom image here is the confidence bounds, that ties in with the statistics. So when you have error bars related to mean flaw size that you can detect, there's going to be confidence bounds. And depending on the technique that's selected, you can have very wide confidence bounds or very narrow confidence bounds. So if it's for military or some type of critical application, that you want to have tight confidence bounds. You don't want to have a lot of scatter in the data, because the scatter in the data can also mean that you can have embedded defect or a missed detection. The general, for people who are course 3 material scientists, one of the best resources for you if in your own research you want to add things related to statistics and confidence levels is ASM Handbook Volume 17. So ASM is the American Society of Metals. They come out with various handbooks. So now I think they're up to 24 or 25 different volumes. So there's an entire volume dedicated just to non-destructive testing and reliability of inspections. All right, the probability of detection, POD, it's characterized by the flaw size, all right? This ties into the CT sample and the fracture mechanics. That flaw size is an input into your fracture mechanics models, and it's one of the critical inputs that all of the output from any computer simulations, whether you're doing finite element modeling or whether you're doing remnant life prediction using some other software or just by hand, that flaw size, that initial crack flaw size that you put in A, is one of the critical inputs. So depending on how reliably you can say what that value is, it affects what the output from those finite element models will be, okay? So that probability of detection, it's a function. It can be determined two different ways. You can do a probability of detection test where it's a simple hit or miss. You either see the flaw or you don't see the flaw. So it's binary. It's like a 1 or 0. The other way you can do is based on a signal response from a known standard. So this is where the calibration ties in. The quality of the calibration when you're doing what's referred to as A versus A hat test. The calibration of the equipment as well as the quality of level of the inspector doing the test and the reliability of the system you're using tie into play when you're doing the A versus A hat. So you can think of that A versus A hat as you have a calibration standard, whether it's a certified block from NIST, which is National Institute of Standards Technologies. That will essentially be the standard that you're basing your inspection against. That's your reference standard, all right? That is where it comes into play for ultrasonics, because for ultrasonics, depending on the material, you can get a calibration block, but that calibration block needs to be based on the material, all right? When you base it on the material, that's how, for ultrasonics, they do what's known as a decibel drop.
Why is it not just geometric? Because a crack is a crack. Why is it?
Well, it's not, because it's whether you're looking for surface flaw or subsurface flaw. So when we talk about eddy current technique in one of the later lectures, the eddy current technique is specifically applicable to surface and near surface cracks, all right, that break through the surface. And those are very small sizes. When we're talking about ultrasonics, we're more concerned with embedded defects within a certain component, regardless of geometry, that can act as stress concentrator where a crack will start. That'll be the weak spot in the component. So there is a difference between whether you want to use a surface technique or a subsurface technique. All right. Probability of detection is essentially a cumulative distribution function. I don't want to get into too much math, but if you went to the ASM handbook, you can read, there's an entire section on the mathematics behind probability of detection. So essentially you have a cumulative distribution function. So it's based on, for the top example, it is based on a conditional probability of the crack being at a random location. It assumes that you don't know where in the component the crack will be. For original equipment manufacturer, for somebody who actually makes the component, based on their designs, they'll generally have an idea on where the highest stress locations will be, whether it's near a weld, whether it's near a double curvature, whether it's near a taper. That's dependent on the component. So that's something where, being the person who manufactures the component, you have the idea where to concentrate where generally you'll know where the weak spots in the design are. Using this formula, it assumes that it's just a random discontinuity that can be, typically this formula is relevant for surface breaking flaws, but ultrasonics, it can be subsurface. So the formula itself is basically what's known as conditional probability, all right? And then as you do more and more inspections, you get what's known as Bayesian updating. So it's the a priori knowledge. So at first they assume no knowledge on where potential flaw may be. As you start doing more and more inspections and you find that there are flaws in certain spots, you update that conditional probability, and that lets you zero in and focus on where you need to concentrate your inspections on. So for turbine blades, they know foreign object damage will be on the outer surface. They know issues with cooling channels will be on the inner surface. So depending on if the manufacturer knows there's problems with cooling channels, they'll know whether to use an eddy current versus another technique. So that's the guideline, right? Where do you want to focus in on the inspection? So the history of the ultrasonics, okay? Before we go into the history of the ultrasonics,
What is the difference in price roughly of the two techniques? I mean, because of course they have different times, different time scales. So including like a factory that is producing something continuous, and so it needs to slow down the production in order to have the testing. How much does increase the cost of production? Check your materials.
so the cost of the inspection, one of the main drivers for the cost of the inspection is the criticality of the structure. So if this is going to be something that's going out to space, onto the International Space Station, they're going to be willing to pay more to do the non-destructive evaluation on it. All right. If this is something that you can go buy at Home Depot for $2, it's the throughput. So, and oftentimes when you're buying something, say it's a plumbing component or something like that, they will, out of 1,000 samples, they will do a random batch sampling where they either do 1 out of 1,000 or 10 out of 1,000 of that batch. So that's where it ties into the billet. When you have a billet, how many components can you make out of the billet? If you can make 50 components out of the billet, you may only test 1 if it's not a high value part. If it's something that is going to be needed for, if it's, say it was a radome or something that's going to be used for guidance missile system, things like that, the criticality of the structure dictates how much you're going to be willing to pay. So, I'm trying not to get too mathematically intense here, but we're talking about ultrasonics. The main thing, ultrasonics are typically used as for when you have to penetrate into deeper samples, thickness-wise. All right. So you have the main equations are the wavelength equals the material sound velocity over the frequency. All right. Very simple equations. But then when you start to think about additional considerations from materials science perspective, additional considerations come into play, and that comes into the time required to do a complete cycle, whether it's a longitudinal cycle, so now we're talking wave propagation, whether it's a longitudinal wave, a shear wave, something else. You also have the wavelength is equal to the material sound velocity times the time to complete one cycle. So for the material scientists and mechanical engineers, the way I can explain it is if you know the material you have, all right, if we go down to where the grain structure is, if we're talking about, separate grains in a material versus single crystal, what happens is as you send those sound waves into the material, they're going to scatter, attenuate, interact at that nano level, okay? That's where it becomes necessary to know the factors of the material under test, all right? So for aluminum, you have a longitudinal velocity and you have shear velocities, and it ties in with your acoustic impedance. So depending on the material you're trying to test, the values change, and these become inputs now that certain types of ultrasonic equipment is being automated, and all you have to do is say into the input into the equipment what material you're testing. This is already preloaded. These values are already preloaded into the NDE equipment. So for critical applications, just saying aluminum isn't good enough. You'd have to know it was aluminum 6061 with a T6 temper. So these are things where the material science comes into play for the inspection. We'll see in some later slides, for ultrasonics, initially, a lot of the ultrasonic techniques came about where it was immersed in water. So we're talking about calibration and reference standards. What you'll typically see is water at 20 degrees Celsius used as that reference. So in some of the later images, I'll show you these immersion baths. If the water wasn't at the 20 degrees, if it was boiling or at a higher temperature, this value will change. So these are things that, if it's a critical application, knowing, if you have to use a specific couplant for the inspection, you'd have to manually go in and change some of these values rather than saying you just go in, buy some equipment off the shelf. You would need to know the materials if it's for a critical application. If it was just for an inspection of a weld on a beam, whether you use the couplant that the company wants to sell you or whether you use some other type of couplant, generally won't have much effect on whether you'd be able to see the flaw or not. The acoustic impedance, that also ties in with the forms of noise. So that will tie in with forms of electrical noise as well. So electrical noise from the transducer into the box, the system itself. So Lord Rayleigh, 1870, the initial fundamental principles of sound propagation and acoustics came about. 10 years later, the Curies published on the piezoelectric effect. So in that booklet on the transducers I showed you, essentially that's a piezoelectric ceramic transducer, and that's what's generating the pulse that will send the sound wave. So when the Industrial Revolution came about around the world, and whether it was in the railroads, they used to just take a mallet and hit the part, and if it didn't sound right, just because the technology wasn't there, you could by hearing it alone, if you hit it with the mallet and it didn't sound appropriate, they'd say, all right, let's pull that one out. So that's how simple the inspection used to be. Now it's gotten much more complex as the computing power and the inputs are able to be programmed into these systems. One of the interesting things that got ultrasonic industry going was the sinking of the Titanic. And it was this is where some of the initial inventions and patents related to sonar came about, to see where could they find, the Titanic sunk, and then they said, where did they try to find it? They had a general idea, but if you're out in the ocean, you have waves, and this happened recently been trying to find the MH370 plane that got shot down over Ukraine. So they know the plane got shot down, but where's the starting point? Are your starting point the entire ocean, or is the starting point something the size of a lake? So when you have no idea where the part you want to find is, the sonar is important. So technologies related before World War I, World War II really dictated where the NDE industry went. In the early 1940s, there's a guy named Floyd Firestone. He developed the first pulse echo instrument. And then a couple years later, there was a different individual who was able to take that idea of the pulse echo instrument and make it more compact onto a single probe. So some of the terms you'll hear in the ultrasonics industry are pulse echo pitch catch, and back wall reflection, time of flight diffraction. So it relates to the time it takes for that sound wave to go hit to through the component you want to test and come back to the equipment. And then in the 40s, was the first practical immersion testing system for unit components that the system stays in one spot and then you can put various components in and do the inspection. When we're talking about ultrasonics, there's 3 ranges of ultrasonics. So ultrasonics is defined as a frequency higher than what the human ear can hear. Now, just because it's defined as the frequency of what the human ear can hear, that's generally not the frequency used to inspect metallic components. When you're talking about metallic components, you want to have a higher frequency because the higher frequency will allow you to get more penetration into the sample. So depending on the longest dimension of the sample, the structural sample you want to test, if it's a very long sample thickness-wise, you're going to want to increase that frequency to begin with. Otherwise, you will not be able to penetrate through that whole sample. There's ways to play around with that. If you use shear waves instead of longitudinal waves, you can try to catch flaws at different orientations. So, but in general, when you're thinking of ultrasonic testing for bridges or other components, if we're talking about rail, they actually have what's called a Sperry car, and it is a train car that sits on top of the rail, and it has ultrasonic transducers that point down at the rail right-of-way, and it does basically an inline inspection at night when certain train lines are out of service. So if the T isn't running from 2 a.m. to 5 a.m., sometimes if you take the T into campus, you will see some cars on like the side of the train. Those cars actually go in at night and do ultrasonic tests all through the railroads around America and the world.
I guess just wanted to, why is it that a lower or a higher frequency means you penetrate deeper? Because like, don't you attenuate more the lower frequency or higher frequency?
Well, it's a trade-off between the resolution of the inspection and the penetration. So it goes to the longest dimension, all right? What's the distance that it has to travel and come back?
So does like higher frequency mean more penetration or more resolution?
Higher frequency means it can penetrate further in, but it sacrifices the resolution of the inspection.
Why does it penetrate further?
If you think of it as a beam, if the beam was focused, the further it has to travel through a thick sample, the more it will attenuate and the beam will scatter. So you want to ensure that the beam hits the back wall and comes back. But if you have an ultrasonically noisy material such as titanium or aluminum and it's thick sample, you have to recognize that the resolution, the flaw size that you can detect will be greater than if it was not an ultrasonically noisy material. So it's a trade-off between how deep you want to penetrate into the sample and how small a flaw size you are required to detect.
So if you say that you're measuring the megahertz, few megahertz, and your wave speed through most materials is a few thousand meters per second, that puts you about a millimeter for the wavelength. How are you going to see defects that are much smaller than the wavelength?
That's when you tie in shear waves.
Shear waves a little bit slower, but only by like a factor of 2 or 3. So if you want to see a 10 thou crack, that's a quarter millimeter. Could be significantly below your wavelength.
And that's where it ties into the confidence level. So rather than it being a 95 POD 90 CL for confidence level, your confidence level may only be 80% if you're trying to find something that's only mils in flaw size.
So why don't people go to like extremely high frequency? If you could get 100 megahertz transducer and sensor,
Yeah, so
use it.
for carbon fiber composites, if you're trying to find a delamination or a debond, say, they do go up to hundreds of megahertz.
Okay.
So that's where the material, and that's where if it's dissimilar materials in intimate contact with each other, if you're looking for a delamination, they can go up above 400 megahertz for those types of inspections. So, but for metals, most of the inspections I've done are 5 megahertz, 10 megahertz, 20 megahertz for something that's either a mild steel or a aluminum type sample. To your question there, it ties back into the direction of the wave propagation. So for a longitudinal scan, where it's basically you're just sending the wave straight in, it's hitting a back wall and coming back, that's the direction of the wave propagation. There's ways to play around with the inspections if you wanted to try to find smaller flaw size. And that's where they can tie in the shear waves, and they can actually use different types of wedges and transducers for the equipment to try to get more sensitivity. I'll hand this out. This actually has some information in here on your question related to transducers, and certain transducers operate in certain ranges. So one of the other things tying into your question is if you wanted to use a transducer at over 100 megahertz, at some point you have to change the piezoelectric that you're going to use. So you have to design an entirely different transducer if you were searching for a delamination in a carbon fiber versus if you're looking for something in metal. All right, the frequency ranges, as I said before, you have subsonic range. There are techniques that operate in the subsonic range. I'm not really going to discuss those in depth. We're more concerned for metallic components, your high frequency, and then acoustic microscopy ranges. So one of the ways, and if I get to it today, I'll show you the slide. There was a service provider on the North Shore, and they do just acoustic microscopy. So I'll show you one of the images, and you'll see that you can actually see the noise in the image. So you have what's called A scan, B scan, and C scan. The A scan is simply the amplitude versus time. All right, it's like the sine wave. The B scan is when you add in another variable, so it would be with thickness. And then the C scan is if you want to actually image it, and that is when you can actually try to size the flaw or locate the depth. So we discussed most of this already. The main advantage is that it can find deeper internal flaws. So if you were trying to find like thousandths of an inch or mils, right? You would generally use an eddy current technique if you knew it was a surface flaw. So say you did a shot peening or some type of laser operation to get a compressive residual stress layer in the component, like they do with glass, right? You have a compressive layer. What you would do with that would be you can use the eddy current technique for metals to find those very small flaw sizes. But the trade-off with that is you cannot penetrate deep into the sample. So you can only go 1 to 2 millimeters depth from the surface. With the ultrasonics, it's essentially the opposite. You can go very deep into the sample because it's operating on the acoustic spectrum rather than electromagnetic spectrum. So the image you're seeing here, this piece of equipment was at UMass Dartmouth, and this was the immersion UT bath that I showed in last week's example. So the samples that I did some experiments on, that is either a titanium alloy or a nickel-based superalloy. And for the NDE industry, what they generally use is called FBH, flat bottom holes. So that they go by 1/64 of an inch. So if you see that 1, 2, 3, below that, they're actually laser drilled holes into those samples of various flat bottom hole sizes. So this is essentially what would be something like a calibration block for that material. And then what you're seeing on the right that is the UT transducer, and how it operates is it actually rasters in the XY direction, and it goes over the, over the surface. That surface is being inspected, and then your data output is basically a color graph showing where the holes are versus where the base metal is. All right, for shear waves, they actually come in and they penetrate through the sample at an angle. So when you would actually look at the image, if we're talking phased array ultrasonics, that's what's known as the sectorial scan. So it basically is an arc length, and it's a slice through the arc length. And that's why, even though you can detect the flaw, you can't generally size it properly because it will appear elliptical because of the shear wave. So I had said last week with phased array ultrasonics, it's basically taking that traditional raster probe in the XY, and the only difference is now they can, using the computing power, they can time the sequence at which each transducer element pulses. So rather than a single transducer element that you saw in the previous image, now you can have 16 to 64 different transducer elements, and you can pulse them, and that way you can then use this T value to say you can get more inspection opportunities at simultaneous time. So what they do is they actually sweep the ultrasonic wave at different angles through the component. So the simplest example is if you went to if you had a pregnant woman and she's going in the hospital, the technology is essentially the same as what they do for sonograms. So these samples here, what you're going to see is they're referred to as wedding cake samples. So there's multiple flaws on multiple layers. And you can see that these were laser drilled in. These are flat bottom holes. These are what's known as side drilled holes. And for the technique, ultrasonic technique, what occurred for the inspections was you put the probe or wedge on the surface, and it can go through at different angles. So now you have issues with tapered double curvature geometry, and you have issues that there's different thicknesses on the different levels. So this was part of one of my theses, and it was how many different types of inspection opportunities can you simultaneously get at once? And then when you take into the material, the geometry considerations, you can actually get multiple opportunities from a single scan. All right, the other thing that is important is it is material specific. So when you're doing an immersion technique, you have to make sure that the material won't be corrosive to the water. So it's actually something that I said, well, this is a mild steel, 8620 steel. So you see the difference for an aerospace application. That's why it would be critical to know if any of those alloys in that engine could corrode. So even though you can do the inspection underwater in an immersion technique, sometimes you would have to sacrifice the entire part to do the inspection. So this one's a little heavy, so. All right, this was an automated immersion system. It was out at University of Dayton Research Institute. That's basically, where Wright-Patterson Air Force Base is. This was a program. They were doing inspection of discs and blades and trying to automate the UT process. So the only thing the human does for this inspection is they put the sample in that middle of where that X is, and then robots, it's essentially a 6 or 7 axis arm movable machine, and the machine itself locates the ID, and this was all automated inspection. So other than a human placing the sample there was no human putting their hands on the sample. It was essentially done automated with robotic techniques and computers. But before you can do the inspection with an automated method, you would have to generate, and a human has to generate that scan plan, and the scan plan is specific to the component being tested. So if you had the scan plan inappropriately, you wouldn't get full coverage. Even though the geometries of those samples are the same and the flaw types are the same on the different levels, that if the scan plan is not correct, you have no confidence in the inspection if you try to automate everything. So the scan plan is very critical when you're talking about automation. All right, when it's something where you can have an inspector actually use a wedge and a probe and manually inspect the component, what you're seeing here is the couple, he's putting couplant on the sample. So rather than it being immersed in water, you use something like a jelly or some other type of lubricant. All right, then what he has in his left hand is the wedge and the probe. So what you're going to see, I have a video to show, but this is the output from that system, and that's a phased array ultrasonic system that was shooting either 16 or 32 transducer probes simultaneously. This is the sectorial scan that, as he's coming in at an angle with the wedge. But what you're seeing on the left of the image is the A-scan data. That's your gated signal. So the individual, what they do in ultrasonics, they typically say a 6 decibel or a 12 decibel drop is what the threshold will be for a go, no go. So if there's a flaw or no flaw, somebody sets that level of decibel drop. So what you're seeing on the left is the A-scan information on what was the amplitude at that location, what was the decibels. And then what you're seeing on the right is the S-scan output after the equipment processes all the various pulsed UT data. So before we're finished, I do want to show a video of the inspection. So what you're seeing on the left, that's where there's noise. There's noise occurring where that amplitude is jumping around just based on the noise in the electronics. So when you have the probe on the sample versus when you have the probe just in air, you can actually see some movement in the amplitude. And the sample that he was testing right there, that was an embedded flaw on the left, and it was not done purposely. So it was in the lab over here. It was machining the sample and trying to bore out the center of the sample, and the tip for the blade that was used for the boring actually broke off during while it was on the lathe, and it got embedded into the test sample. So rather than tossing the test sample out, I said, well, now we can actually see it actually fused the blade. The cutting blade actually fused within the sample. And it was interesting because you could essentially see not only the embedded flaw, but you could see from the heat of the fusion that there was essentially what would be something like a heat affected zone from the heat of it breaking off in the sample. So that was one of the samples that was being tested, and that is the equipment on the upper right with a various probe and wedge that was selected. So we did it at a couple frequencies, 5 megahertz, 10 megahertz, and maybe 17 or 18 megahertz to see at different frequencies how the resolution and the data in the output changed. So, let's see if there's anything else. The last thing I just want to touch upon, when you're doing biological samples or you're doing samples where you're not concerned with macro size flaws, but micro scale or mesoscale, acoustic microscopy would be a better technique for if you're looking for micro scale, all right, because you can operate it at lower frequencies but higher resolution. So, but what you're seeing in the image here that I wanted to point out was there's quite a bit of noise in the output. So there is a trade-off between the noise that you can accept in the output versus if you just want to see if there's a flaw or no flaw. So that's the hit-miss data versus A hat. There's two different ways to do the statistics to get that 95-90 values. So depending on which one you choose, the options are you can either do a whole bunch of experiments or you can do less experiments with more opportunities on each sample. So we're out of time for today, but if you guys have additional questions, I do have some other videos of UT testing being done. If you're interested in them, let me know, and we can continue some of this tomorrow as well. Tomorrow's lecture is going to be radiography.